Okay, so 11.2, arc length and speed, just a quick summary. So now that I'm recording, we are looking to increase the number of points that we use for this approximation so that it gets more and more accurate. The larger, or as n approaches infinity, of course, we get to be a perfect fit for this arc length. This is something that we can take and then find surface area and things like that with it. So here's our formula, right? It's given. Of course, it's proven elsewhere, but for today, we're just going to take a look at it as the given. So C of t, the parametric form, is x of t, y of t, where x prime of t and y prime of t exist and are continuous, as always. Then the arc length is given as the integral from a to b of the square root of x prime squared plus y prime squared. So example 1 is asking us to use this equation 3 to calculate the arc length of a circle with a radius r. Okay, so we can use, right, the x equaling r cos theta and the y equaling r sine theta. R is completely arbitrary here. It could really take on any value, any positive value, and we could prove this the same way. So it tends to be easier in this section because, right, that formula is a little complex, and there's going to be times when you're going to want to simplify the inside of the square root before you go to the square root, before you go to the integral, etc. So sometimes in this example, it is helpful to do side work. So I tend to do it on these, but you don't have to. Everything could go right into the formula from the start. So just remembering, I need the x prime, I need the y prime, and I'm going to square both of them. Right. So I end up with, when I derive r cos, I have negative r sine, which is then squared. When I derive r sine theta, I get r cos theta, which is squared. There will be several times throughout here and moving through this chapter where we do pull some trig identities. So sometimes they're as easy as the sine squared plus cosine squared. Sometimes they're not as easy as those. But ultimately I have an r squared that I could factor out from both of those terms. So then I'm just looking at an r squared times 1 or r squared. So now that I've got this super easy inside of my square root, then I can go to my formula. S arc length equals the integral from a to b, or 0 to 2 pi I should do, of the square root of r squared, d theta, which of course the square root of r squared is just r. Right? Which would then integrate, antiderive to r theta. R is still just a constant from 0 to 2 pi. Evaluate f of b minus f of a, and you get 2 pi r. So the second one goes to 0. Nico.
Why isn't there's a d theta, so when you integrate from 0 to 2 pi, so why isn't that like d2?
Only because I used theta as my because we're talking about cosine sine. I could have done cos t. So my parameter, good question, my parameter is not t here. Your parameter doesn't have to be t. The parameter is a third variable,
Yeah.
term, way to compare x and y. So I could use t for sure, but since it's an angle, I might as well use theta. That's all. A lot of times we do use t because we're talking about time. In this case, I wasn't talking about time. Okay?
Is there a reason your final answer is equal to the diameter of the circle? Is that just a coincidence?
Is it the diameter?
Arc length from 0 to 2 pi is the circumference.
Circumference.
I'm sorry. Oh my god.
No, but it's good. You made the connection that we want to make. In your head, it was the right connection. It just didn't come out that way. Exactly. The arc length of a circle all the way around is our circumference formula. That's exactly what this is proving, which is why the r is, of course, arbitrary. This would still be valid for any radius, right? We would be able to find the circumference of anything, of any circle.
So basically, like when we're doing the integral, it doesn't matter because r is a constant.
In this, not always, but for this
For this
example, to prove it, correct, because we're talking about a circle. That's a proven formula. Maybe proven using this. I don't know exactly where 2 pi r originally came from, but it certainly is confirmed with this idea, right? Okay, length of a cycloid. So here we go, Tyler, back at you. We want to calculate the length of one arch of the cycloid generated by a circle of radius r is equal to 2. And they're saying see figure 2. I'll do an okay job of giving you a rough sketch of what figure 2 looked like. Drawing a circle is the hardest part for me because, I don't know, you see the point on there, you see the center, and like just trying to center it roughly is hard. Okay, so that's what it looks like, right? It's I want to say it's rolling. It's like you're taking a ball and you're pushing it and it's rolling, right? So calculating the length, we're back to, we need to get back to that arc length formula. So thinking about things that we're going to need, we need x of t, right? This example from the book chose to keep it as t. You could go to theta. It doesn't matter. So I'm going to do t this time. X of t is equal to 2 times t minus sine t. And Tyler, are these the equations that you were talking about, these parameters? What?
Yeah.
Okay, then yes to that question. I didn't know if you were talking about the specific example that got a little bit more complicated. These are coming from, I'd have to pull up the textbook. They are coming from the last section. Let me see. I don't know if I grabbed it when I did mine. So the r being 2 is there, and then we're looking for that t minus sine t rule. Yeah, that is equation 5 under that word I couldn't say yesterday or Monday, parametrizing the cycloid. X of t, equation 5 says x of t is equal to t minus sine t, and y of t minus, or equals 1 minus cosine t. And then equation 6, if you then have a given r or a given center, or no, r, I'm sorry, r for this one, then you can have the 2 out in front as it is, or the 2 distributed in. So equations 5 and 6 from section 11.1.
That's something you have to memorize, right?
Yes, so if, back to Tyler's first question, those you do have to know. Add it to the list, people. I am sorry, I am just the messenger. All right, so we've got them. We need to derive them. So we would have 2 times 1 minus cos t, and y prime is 2 times positive sine t. Right. Next level, I need to square both of them and add them together. So we have 2 times 1 minus cos t squared and 2 sine t squared. We want to see where this takes us. We're going to have to FOIL out the 1 minus cos t. I'm going to keep the 4 out in front. So I have a 1 minus 2 cos t's plus a cos squared t. And then I have plus a 4 sine squared t. Right? Okay, so now I'm going to distribute my 4. I can factor the 4 out of just the second 2, right? Because then I have my identity down there. And of course, I'm acknowledging that this manipulation in this section is where some of the creativity comes in. You have to start to see that stuff. I think we're all, really comfortable with sine squared plus cos squared. Some of the others, maybe not so much. So another one that's going to come up, and this is in the side page, it's reminding us that 1 minus cos t over 2 is equivalent to sine squared of t over 2. So that was a side note reminding us of this. And so we actually do have this. The first thing I make sure I show, it's 8 minus 8 cos t, which I can write most naturally as 8 times 1 minus cos t, which 1 minus cos t isn't super helpful. So if I pull out another factor of 2, I would then have 16 times 1 minus cos t over 2. Right? That's definitely a jump. That's not some... What's that?
Do we need to convert that to sine squared t over
Yes, and now we convert that to sine squared t over 2.
Well, you could have just kept the 8 times 1 minus cos t because you could just multiply.
I could have multiplied it over by 2. But just even thinking that I need that identity without it being given to me would have been a challenge. For me, at least. I'll openly admit that. So you have 16 times sine squared t over 2. Right?
What do you want? Just
Where am I going with this?
yeah.
Right? I am just working on simplifying inside of the arc length formula.
Okay.
Because if I had all of this written as my integral from a to b, square root, it would just be a lot. It would be a mess. And really, I want to get to something that I can actually square root. Because otherwise, if I'm trying to integrate that mess, then it's a crazy u sub that's maybe not possible, or just, something that I can't do. Okay?
So 1 minus cos t over 2 is equal to sine squared t over 2. It's an identity, right?
Correct.
Okay.
Correct. So
You
now,
need to memorize them.
yeah, you have to have some of that kind of stuff in the back of your mind. So now, I've simplified it enough that I can go to my arc length, 0 to 2 pi, of square root 16 sine squared of t over 2 dt.
Wait, isn't it 4 pi?
What did I forget? Why are you saying that? Okay, good question. I'm glad you said that to me. What am I integrating with respect to?
Theta. Wait,
I didn't, T. So you might not have seen it, but I'm still glad you asked the question. It's 4 pi along the x-axis, but t is equal to 2 pi at that moment. So really relevant question, right? Does everybody understand the difference? I'm integrating with respect to t here, so I want to make sure that I have using those parameters, okay? Thank you, Tyler, for asking that. All right, so I can square root that very easily, right? And then I have the integral 0 to 2 pi of just 4 sine of t over 2 dt, right? So I can, of course, anti-derive my sine. I can just deal with this with a linear chain rule shortcut, right? If it's linear on the inside, I divide by that 1/2 to undo that. So this would go to negative 8 cos of t over 2 from 0 to 2 pi. And then evaluated at 2 pi, divide by 2 is pi. Cos at pi is negative 1, so you get a positive 8. Cos at 0 is positive 1, so you get minus the negative 8, so you do get 16 there. Okay.
Would you please clarify what are we trying to find?
Yep.
Like, are we trying to find a singular function?
So that is not a singular function. That is the arc length. That's kind of like the distance traveled, but with respect.
My apologies. I meant to. I knew we were solving this wrong. Like, what made us want to get to the 16 sine squared?
Gotcha.
T over
Yep. So anytime we've been dealing with whatever functions, right, and we're putting multiple parts together, for example, whatever the content is in this case, we always want to make it the easiest form. You know, a final step is the integral. Before the integral, I have to square root. So if all I'm doing is simplifying before I plug it into the more complicated part of it. So I'm taking the pieces that I know I need, the x prime squared, the y prime squared, seeing if I can simplify it to something that I can further simplify before I integrate. That's all that pre-work. Because if I just started my work with the whole formula filled in, for me at least, it'd be, you can, but it would be more daunting. I might get lost in the work. I might copy something down wrong. And I might also, from the very beginning, be like, how the heck am I going to integrate this? But I'm not ready to integrate it yet. I need to simplify it first.
Okay. And then second question, I must have blanked. But where did you get the x of t is equal to 2t minus sine?
Good question. So equations 5 and 6 from section 11.1 is from the cycloid. And specifically because the r is 2, we're using equation 6 with r being 2.
Got it.
Cool. You're welcome. Okay. Speed along a parametrized path. The derivative, right, ds over dt, is just the inside of that integral. Right? We don't want to add everything up. We want to derive the integral, so we're just looking at that square root portion. Okay? Cool, so example here. I'm going to speed myself up a little bit, not a play on words intended at least. So a particle travels along the path c of t equals 2t, comma 1 plus t to the 3 halves. Very straightforward question here. Find a, the particle's speed at t equals 1. Okay, so we use the formula. and then we plug in 1. Right, so we need our x prime of t and our y prime of t. X prime is just 2. Y prime is 3/2 t to the 1/2. So therefore, speed, using the formula, is the square root of 2 squared plus 3/2 t to the 1/2 squared. You can put your value of 1 in there right away. You can simplify. That's entirely up to you. I'm going to simplify only because sometimes problems like this have us using this for multiple values of t, so might as well make it nice.
Was it 2 squared or?
No, the derivative, 2 squared.
Oh,
So in general, my speed is going to be found by just the square root of 4 plus 9/4 t, square root of that. And specifically, s prime at 1, which is our speed, would just be the square root of 4 plus 9/4, which is 2.5 meters per minute. Okay? Nice to have a very straightforward, simple question every once in a while. The distance traveled, s, and the displacement, d, during the interval from 0 to 4. What are they asking us to do?
Find the integral.
Yeah, find the integral of, sorry, go ahead, say it again.
Find the integral, I believe, of the arc length from 0 to 4.
Yeah.
I know.
Cool. You can say it that way, absolutely, or the integral of the speed. Either way is totally fine, right? The whole idea of integration was adding things up. So if I know that I'm traveling at a certain speed for a certain amount of time, then that's going to give me my total distance traveled. So it's right back to that. So part B is just simply put, integral 0 to 4, square root 4 plus 9/4 t dt. So it's a linear chain rule that we're undoing here, not bad. So we are getting, right, 2/3, because it's going to 3/2, dividing by 3/2, and a 4/9, so we're dividing by 9/4, so multiplying by 4/9, inside to the 3/2 from 0 to 4, which is 8/27 4 plus 9/4 times 4 to the 3/2. Oh no, I didn't put the parentheses correct. I'm going to pull the 8/27s out. Minus 4 plus 0 to the 3/2.
Why did you multiply by 4/9? Isn't it just 2/3?
Remember that it's a linear chain rule happening as well. So to
Oh,
all right, so simplifying all of this, it doesn't come out nicely at the end. The decimal answer is 11.52, and meters was our unit. Okay, good. I'll leave it for another minute for copying. We have 2 more examples in this section, and then just a couple in the next one, polar coordinates. Okay, so our next example uses the idea of angular velocity. So it's straight from physics. I don't have the figure copied down, I'm sorry, but there is figure 5 in the book I'm referencing. We don't directly need it, but that's where I'm pulling information from, and the relationship from physics with this angular velocity W. It's not really a W, I get that. Does anybody know? What is it? Omega, thank you.
Omega.
Omega, thank you. My physics colleagues won't be happy with me. Omega. So it's r cosine omega t, comma, r sine omega t. And many of you probably are very familiar with it. Physics classes.
This is a physics one, or physics.
So from physics.
It's physics one, from what I
So this is physics 1, so everybody should be comfortable with it. Is that a fair statement?
You can just use the physics formula, which is angular velocity is linear velocity over radius,
Yeah, yeah.
and then you just multiply the angular velocity by the radius, and you get your answer.
I never took, quick snippet, never took physics here when I was here. I only took it in college. And not that I didn't enjoy it, but I haven't had it since, obviously.
Could you zoom in on that? I can't.
On what I wrote or on the,
What you just wrote.
so it says C of t equals r cosine omega t, comma, r sine omega t.
What exactly is omega?
Ooh, that's the physics lesson coming in.
Angular velocity.
It is the angular velocity. And in terms of what we need it for, it will say that, right here in the word problem, it will tell us what it is, but where that parametric equation came from, that comes from physics. Okay, that relationship.
Yeah, but like for these problems, like if you see it on the AP exam, like it would be so much quicker if you use the physics formula, which is just like velocity is angular velocity.
Yeah, I don't think
Your
we need to
velocity
use
is
that
angular
in
velocity
physics.
times radius, and then so you get it in like 10 seconds.
No, it's omega is equal to b.
How about,
over r.
can I do it the way that I've got it here, and then one of you do it, or maybe if we have time, talk about it, because I think some of us from the physics perspective, like maybe Debbie is on my side, I don't know totally what you're referring to, but I don't disagree that you probably have a better approach. So I'm going to show you the calculus approach, and if on the AP or on my test or wherever, using the physics approach is better, by all means go for it. And maybe we'll save that conversation when we're into the review. Okay. So for this example, I've got my parametric equation, then I need my x prime, right? That omega inside of my cos and inside of my sine create like linear chain rules, right? So my derivative of the r cos omega t becomes negative omega r sine omega t. And my y prime, same idea here, but it's positive omega r cos of omega t. So this problem works out really nicely. So I'm still not disagreeing with your other physics approach, but this will work out easily. So I'm looking for angular velocity, which means I'm looking for speed, right? The s prime. So I don't need my integral. I just need the square root. And in this case, because it works out so nicely, I am putting everything in there. Not a negative, that's wrong. Right? And what happens here? We have omega squared, r squared, and then we have our sine squared plus cosine squared when we factor under the square root. And to call this, our velocity here, our speed, what we have going on, we just need to make sure that we have our angular velocity staying positive. So absolute value times the radius. So in this particular problem, the answer is 3 times 4, or 12.
That's what I got using the physics.
Good.
Yeah,
All right.
so it's omega times radius is linear, is just b, and then.
So this just proved it.
Exactly.
That's all that happened. We proved it. Use that shortcut for. Okay, so now I am seeing the connection. So he's just saying just multiply omega times radius. That's it. Done. Got it. We proved it from the calc perspective. use it from either calc or physics perspective now. Thank you. Appreciate you.
It's really good.
sure that works.
Uh-oh. Surface area. Okay. So let C of t equal that parametric equation, x of t, y of t. Y of t is positive, x of t is increasing, and x prime and y prime are both continuous. Then the surface obtained by rotating that parametric about the x-axis has a surface area. Right, so it's just like that outer shell.
So we're gonna do volume, right?
I haven't prepped volume yet, Mullen. I'm a day ahead of you all, 2 days ahead of you all. No, actually, I don't know. I don't want to speak. I don't remember Mr. Reyes showing me that one. So then the surface obtained by rotating it has this surface area 2 pi times the integral from a to b of y of t times your square root x prime squared plus y prime squared. So in my head, I said, well, I've got the height, like the y of t. I've got that arc length, and then I've got that 2 pi. Right, so it all makes sense. So yes, it's another thing you have to memorize, but conceptually, it's not so bad to recall. This is another one that used some different identities. And this is hyperbolic trig. I know that this example came up way back when, and I think that we concluded, does anybody recall that we didn't cover it? And did you cover it in Pre-Calc Excel?
No.
No.
No way.
Right?
No.
No,
We also didn't do like half the stuff like a one.
I know.
We did like one half.
I know. Okay. So again, this is another, I forget if I asked Mr. Reyes about this or not, but I remember that when we had this example, I forget the section, it was in a different part of the book that we don't cover in our content, but I'm going to double check with him because it could be that it's assumed prior knowledge. And I don't know that answer yet because I'm first year, fourth quarter Pre-Calc Excel teacher. So I don't know the full curriculum of Pre-Calc Excel. I'll answer that question. We'll do this problem because it doesn't really matter. It still is a good example. So calculate the surface area of the surface obtained by rotating the tractress C of t equaling t minus tan ht, comma, secant ht about the x-axis from 0 to pi. Okay. So we've got our formula right above us. We need our x prime, we need our y prime. In the side notes, the identity that they are suggesting to recall is that 1 minus sec h squared t equals tan h squared t, and sec h squared t is obviously then 1 minus tan h squared t. So we've got those. Those aren't bad. All right, so x prime. I guess for me, even if I knew nothing about these, I just have to 100% acknowledge that h is not another variable. It's a different type of trig function. Because I wouldn't want to turn this into a chain rule when it's not supposed to be a chain rule. Like h is not a variable that we don't know about. So x prime of t is 1 minus sec h squared t, and y prime of t is negative sec ht tan ht. Wait, why is it negative? I don't agree with that. Right? Sec goes to positive sec tan.
Yeah.
Are you doing 1 minus sec?
No, because I think I copied it right from the book, but whatever. It's positive. That's not right. Yeah, sec x goes to sec x tan x. Positive. Cosecant is the one that went negative. So I know that that's wrong, whether I just made a quick error when I copied or whatever. But it doesn't matter because we square it anyway. All right, so then we are going to square these. So this is my side work. I don't want to put this mess into the integral. I want to simplify as much as I can before I get there. So I'm going to square the 1 minus sec h squared t, and I'm going to square the sec ht tan ht. So that means I'm going to get, right, if I,
Tan HT mean again?
it's a hyperbolic tan.
Okay, oh yeah.
Beyond that, I don't have a good explanation for you.
So do we, so
That's what I'm going to find out. If you need to be more in depth about what a hyperbolic trig is.
So for now, all I have to know is that it works just like tan.
Yes, for right now, h is not another variable. It's just a different form of
Tan.
tan. Okay?
All the identities work the same.
Yes.
Okay.
All right. So I'm going to swap out the 1 minus sec squared to the tan h squared t. And I am going to acknowledge that if I distribute my squared, I have sec h squared t tan h squared t, right? So I substituted in the first one, and I put the squared into each individual term in the second one.
Wait, isn't the first one, isn't that the fourth?
Oh, I dropped the squared. I didn't mean to. I haven't squared it yet. Or yes, or to the fourth. So either way, thank you. So yes, I have a tan h to the fourth t. Now I'm going to replace the other sec with the tan so that we're all tan. Haha, Nico's tan. No, it was a conversation me and Nico had before, but it was perfect. Sorry. We have 1 minus tan h squared t. You have to laugh when you do this stuff. Times tan h squared t. All right, cool. The great thing, we're getting there, because now if I distribute the 1 minus tan h squared t to the other tan h squared t, things cancel. And when things cancel, life is so much easier. So what cancels? Those tan h to the fourth t's cancel out. So I am just left with tan h squared t here. So all that's going into my integral with my square root is that. All right. So I have surface area equaling 2 pi integral 0 to pi, because it told me that, square root of tan h squared t.
Wait, can you explain how you get tan h squared t from that?
Ooh, I forgot something too. Because when you distribute, Moulin, the 1 minus tan h squared t to the other tan h squared t, over here, I'm going to get a tan h squared t and a minus tan h to the fourth t.
Makes sense.
Gone. Okay, I forgot the y of t going in here. So my y of t is sec ht square root tan h squared t dt. Cool. All right. Yes.
I was just like following along the textbook, and they're doing an improper integral from 0 to infinity, not like 0 to pi, or maybe that's what your integral says. I can't read it.
I think I said pi, but I wrote infinity. I'm sorry. Yes. I don't know why. Yeah. That's a sloppy infinity symbol, and I did read pi by accident now that you're asking me. Thank you. It is 0 to infinity.
0 to infinity?
Yes, and it is an improper integral. I said pi. I apologize. Probably because I wrote 2 pi prior to that. Anyways, so now we've got our integral. Not so bad, because the wonderful thing that square root of tan h squared goes to a tan h. So we have a secant h t tan h t, which we can easily integrate. So 2 pi, improper integral is correct, 0 to infinity of secant h t tangent h t dt. Right, so we are acknowledging that this is an improper integral. We are going to kind of address it by saying that it is equivalent to 2 pi limit as r goes to infinity, integral 0 to r, again, of that secant h t tan h t, and now we can finally get to our answer. So the limit of that integral, right, this returns to sec from 0 to r. Why is it going back negative? Heidi, you're looking at the textbook, right? Maybe there is a rule with the hyperbolic that's causing it to go negative on us. Because now my work down here is showing that the integral of secant ht tan ht goes to negative secant ht.
Yeah, that's what the textbook says too. I think it's just different for hyperbolic.
It must be. All right, I'm gonna follow up. It's not a game changer for this example. So before it was probably supposed to be a negative up there. So it returns to 2 pi limit as r goes to infinity. I'll write it negative secant ht for now, because obviously it's correct. I just don't know the extent to which you need to know that. And that's going to equal, now if we evaluate this limit, or if we evaluate the r to 0 first, and then the limit, we have a 2 pi limit as r goes to infinity of negative sec r, negative sec hr. The book gives an explanation. I don't have time, I'm sorry. But that portion goes to 0. It just says, see the book. And the sec h at 0 is 1, so we have a final answer of 2 pi times 1, or 2 pi. Okay.
So like when you derive a secant ht times 10 ht, you integrate it. It's just like the rule, right?
Let's just use that for right now. I'm going to follow up with hyperbolic. I promise you that. And by Friday, I'll tell you.
So secant ht times 10 ht just anti-directs to negative secant.
It does antidirect to negative. So the h, the hyperbolic portion of this, has something to do with it. Because if it were not hyperbolic, it would be a positive. Right? Okay, so all of our minds are thinking correctly right now. Like, why is it negative? It's negative because of the hyperbolic. Don't know exactly the extent to which we have to have that for our BC content.
We're gonna learn it Friday?
It's not, no, the hyperbolic is not part of our direct curriculum. It might be stuff that you were supposed to know coming into the class. That's what I have to find out. But nobody seems to have any grasp of hyperbolic at all. Even people that took, like Alex G., you took it over the summer, right? Do you recall going over